All right, welcome back. So today we'll be still in chapter 13, talking about two main topics, ideal gas law and kinematics. So let's jump in. So we are fan of balloons. I don't know if you are, but I am. So balloons is always associated with good things as I can think of, like birthdays, parties, and all sort of celebrations. And there's actually a annual balloon festival in Marysville, Ohio, which is not far away from us. So this year, it typically is in the summer, so you can go Google it and check the dates if you want to go this year. But we humans always have dreams of being flying from ancient times. That a couple hundred years ago, more than a couple hundred years ago, the um, French brothers, Mongolians, and they were the first successful people to able to fly in air for a certain distance of amount of time and distance. And we always try very prior to that, people have tried many times different devices, different ideas, but most of them fail. Back in more than about almost like 2,000 years ago, in ancient China, in the Three Kingdom era, people actually have already used balloons. They call them lanterns, like this, to for military like signaling if the enemy is coming. So using that, so it's back very um, long time ago. And these days, you can buy these type of lanterns. You can set them off if you are celebrating. So my neighbor used to be setting these blue lanterns off on July 4th. You can do that too. You can buy them and then do that. So there's a candle in there. You actually light it up, and then you'll heat up the airs inside it, and then will lift off in that case. So basically, what balloon works is the gas inside it, and um, they are creating. It depends on what kind of gas you have. So a lot of balloons, if you want to set them up, you use helium as the gas inside it. And if you just use normal air, it will not fly off. Or you can like as the hot air balloons, you can heat them up, so then they are becoming lighter. So today we'll be looking into the theoretical background of that. Um, so it's the main subject is the gases here of our interest. So gases are also the easiest state of matter to describe. So in this case, if you can think about gas molecules, so the easiest way to study the gas is a set of gas that can be considered as ideal gas. So then they are far away from each other. You can ignore the interaction between the gas molecules. So like as the figure show on the left, so if they are far away from each other, you can ignore any interactions that is like the figure on the right here shows. So if they're close to each other, then there's attraction or repulsive forces in there involved. Okay. Now, luckily, in the normal scenario, our wrong air can be actually treated as ideal gas because air molecules are farther away from each other enough, so you can consider them as ideal gas. When we describe a collection of gas, we use several physical parameters here. So one is pressure, one, and then temperature, and then volume, and the number of the gas molecules or atoms, depending on what kind of gas you have. Some of them are made of just single atoms, so you can say number of atoms, or some of them are like molecules, like say oxygen is O2, or helium will be just an atom of helium as its molecular. The SI units for these parameters for pressure is Pascal. PA for temperature is Kelvin. For volume is meters cube. It's not liters or centimeter cube. You have to convert it into meters cube. Okay. And number of atoms, you can use moles, or you can just say how many atoms you have. So if you use capital N, that means how many molecules or atoms you have for this particular collection of gas. If you are using small n, then you're talking about how many moles of molecules, which one mole is equal to 6.022 times 10 to the 23rd atoms or molecules. Okay, so let's just dive in here. So normally, if you have temperature increases, the pressure of the enclosed gas. Okay, so we'll be talking about enclosed gas here, will increase. So a setup here, we talked about this last time. So this is a flexible mercury here in this tube here, which you can adjust the surface level of this guy. This should be the flexible part. And then the temperature, if this container is immersed into a bath, and you can fix this left side of the surface, and you can change the temperature, and then you can monitor the pressure, which will be given the height difference of these two surfaces. So as you increase the temperature, this height will increase. Okay, so that means the pressure is going to be proportional to the temperature, given that you have fixed volume here and then fixed number of molecules inside the container here. And depends on different gases, they probably will give you different slope on this pressure versus temperature curve. So P is proportional to the temperature. I'm going to just write this down on my note. So I will switch my camera just briefly. So I'll write down that for the first relationship, P and T, so P is proportional to T for fixed V and number of molecules, okay? And this is what we have for right now. Now move on to here. Now, if you have fixed amount of molecules here, and if temperature is fixed, so if you sit on the ball or you squish the ball, the pressure inside the ball will actually increase. Okay, so then P is actually proportional or inversely proportional to the volume of the gas, okay, for fixed M and temperature. And if you pump into the not fully inflated ball, now the shape is not changing much. So volume is fixed. Temperature, if you are doing this slowly enough, it's not increasing as well. So then as you pump more air molecules into the ball, the pressure inside the ball will also increase. So you can write that P is actually proportional to the number of the molecules for fixed volume and T, okay? So combining these three relationship, we have all on for these three relationships, we all have P in front. You can say P then is proportional to T, right, and N. So you can do N and T, but inversely proportional to V, okay? Or you can say P then is equal to N times T divided by V, and then times a constant number, let's call it K, okay? So then you rearrange. Let me just stop sharing so you can see this in the bigger screen over here. So the first relation was that P is proportional to temperature, pressure is inversely proportional to volume. So you do inverse of volume. And then pressure is proportional to the number of molecules. So then combine those three, pressure should be proportional to the number of molecules, air molecules, temperature, and then inversely proportional to V. And you can write the equation that P then equal to N times T over V times a constant number K, okay? So based on this, then if you multiply both sides by V, you get PV then equals to NKT, okay? So pressure, volume, number of molecules, and temperature. Now this K, the constant, is determined to be just the Boltzmann's constant, okay? So let's go back to the PowerPoint slide. So combining all those three relationships, we can see that pressure is equal to a constant number times N times T over volume. And this K turns out to be, or if we rearrange, multiply both sides by V, you get PV equal to NKT. So this is called the equation of state for the ideal gas, or also called ideal gas law. This constant number turns out to be a constant that we'll see often in physics. It's called Boltzmann constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. Okay, so in that case, so PV then equal to nRT or NKT in this case. Let's take a look on this example here. It says a person's lung can hold about 6 liters of air at body temperature 310 Kelvin and atomic pressure of 101 kilopascal. Given the air is 21% of oxygen, find the number of oxygen molecules in the lungs. All right, so it gives you the volume. So the air in the lung, the volume of the air in the lung, then it's 6.0 liters. Now liters is not a SI unit for the volume, so you do the conversion to meters cubed using this conversion factor. Body temperature is given as the Kelvin, so that's SI unit. Pressure is kilopascal, so you do the conversion from kilopascal to pascal, which is times 1,000. Okay, it's asking the number of air molecules. So we just learned that PV equal to NKT, and K, Boltzmann constant, is a constant. So we can take a look at the solution of this one together. But if you are watching the video, I will actually suggest you guys do this first. So pause the video and see if you can solve this. And then if you can solve it, then you can resume the video and then see what you get compared to with the solution. And if you have tried but still have difficult, then maybe you can also resume the video and then see how this should be solved. Okay. All right. So I'm going to stop sharing the PowerPoint slide. And let's take a look at the solution together. So we know so we can treat because this is the collection of air under normal conditions, so it can be treated as ideal gas. Okay, so then we can use PV equal to NKT, the equation we just learned, where pressure, volume, this is number of air molecules, this is Boltzmann constant, T is the temperature given. Okay, so we are looking for the number of oxygens, and it states that oxygen is air has 21% being oxygen. Okay, so we can find the number of air molecules first and then multiply by 21%. That would be number of the oxygen. So it's basically looking for N here. So you rearrange, you divide both sides by KT, you will have N equals to PV over KT. Okay. So K is given in the problem as 101 per kilo Pascal, so 10 to the third Pascal. Volume is given by in liters. Okay, so you multiply it by 10 to the negative 3 to give you to the meters cubed. And then divide by Boltzmann constant is 1.38 times 10 to the minus 23 joules over Kelvin. And K is given as 310 Kelvin. Okay, so this will give you 1.4, about 1.416 10 to the 23rd air molecules. Okay. Now for number of oxygen molecules, then N, let's say parenthesis of oxygen, there should be 21% of the total N. Okay, so you do 21% times that 1.416, 10 to the 23rd, that will give you about 3.0 times 10 to the 22 air mole, oxygen molecules. Okay, so molecules. All right, so let's go back to the PowerPoint. All right. Now, the number we got, 3.0 times 10 to the 22, is a big number, okay? So then in chemistry, we actually use moles instead of number of molecules. So this is a quick review on what's the how the mole is defined. The mole is the amount of substance that contains as many elementary entity as there are atoms in 12 grams of carbon 12. Okay, so how many atoms of carbon, how many atom carbons in carbon 12 grams of atom, carbon 12 is 1 mole. And that turns out to be 6.022 times 10 to the 23 molecules, okay, in 1 mole. So in that case, mole then is equal to, or the total number of molecules, if you are given n moles, small n moles of gas, then there will be m times this n sub a number, which is 6.022 times 10 to the 23rd of molecules. And this number is called the Avogadro's number. It's also a constant number, okay? So SI unit should be per mole, how many molecules per mole. All right, so if we do that, capital M replaced by small n times n sub a, then the ideal gas law PV equal to NKT. Capital N is small n times NA, NA being a constant number, K being Boltzmann constant number. So these two multiply together, then will become a new constant number, so which is called the universal gas constant. So Na times K Boltzmann constant times the Avogadro's number gives you 8.31 joules per mole times Kelvin. So R is equal to 8.31. So if we do that, if we combine N sub A and K, that gives us R. So then equation of state or ideal gas law becomes PV equal to small n times RT. Okay, so it's either PV equal to NKT or PV equal to nRT. It just depends on what you are looking for. If you are looking for a number of molecules, then you use this equation. Or if you are given a number of molecules, you can use that equation too. If you are looking for or given number of moles, then you use this equation, okay? So two versions of ideal gas law, they are basically the same thing. All right, a second example here, it talks about how many moles of air are in an inflated basketball. Assuming the pressure in the basketball is 159 kilopascal, the temperature is 293 Kelvin, and the diameter of the ball is 23.0 centimeter. So again, we are looking for number of air molecules basically, but now in moles instead of just individual molecules, okay? So in moles, then we'll use the different set of the other set of equation of PV small n RT, okay? So the equation to use for this one will be PV small PV equal to nRT, okay? Instead of last one here is capital N, number of molecules, K, Boltzmann constant times T. But in this case, you're looking for how many air molecules in mole, so we use this equation, okay? So again, you're solving for M, you do both sides divided by RT this time, PV over RT, okay? P is given as 159, again, it's kilo Pascal, so that means 10 to the third Pascal. V, this is the volume. It gives you diameter. So to find the volume of a sphere given diameter, the equation to use is you can do 4/3 of pi r square, right? R square means diameter divided by 2. Radius, r is radius, so that means diameter divided by 2. So diameter is 23.0 centimeter. Again, there's a conversion here. Okay, so that's to the Q should be your volume. Okay, so this is P, this is V, this is volume for uh, a sphere. Pi over 3 or 4 over 3 pi radius square divided by R times Ti is the gas constant 8.31 joules over moles times Kelvin times T, temperature given, that's already in SI unit of Kelvin. Okay, so then this will give you 0.416 mole of air in the ball. Okay, so instead of getting a big number, you are now just getting a smaller number because now this is in moles. Okay, all right, so let's again go back to the PowerPoint, and I'm going to switch back my video. All right. So now let's go back to where we start with the hot air balloon. So how does a hot air balloon work? So this can be analog to if you have empty bottle throw into the water, so you'll be floating. So now here the buoyant force will be larger than the weight of the bottle, right? So then it's floating. But if you start to add like rocks, small rocks or pebbles into the bottle, so the weight will be increasing. Now the buoyant force might be still a little bit larger, but close to the weight of the whole bottle with the pebbles. So it's not still sinking. But if you keep adding more pebbles into the bottle, then the total weight will be larger than the buoyancy force. So then it will sink. Okay, so the same thing here for air molecules for hot balloon. So instead of having pebbles in the bottle, we are now having air molecules in the balloon. Okay, so when you there's an opening at the bottom of the hot air balloon here, so the pressure inside the balloon and outside should be the same because they are connected. So then the pressure is constant. The volume of the balloon is not changing. So these two are not changing. So then N times R times T, if T is bigger, then you have smaller N. So that means there's less molecules inside the balloon. So the total weight of the balloon plus the air is smaller, right? Now, if you decrease the balloon, in that case, then the buoyancy force by air to the balloon might be bigger than the total weight. So then it will lift up. But if you decrease the temperature of the air inside here, then this guy decreases and increases. So now you have more air molecules inside the balloon. So the total weight is larger than the buoyancy force. So then this balloon will descend. Okay, so you can control the temperature of the air in the balloon, then you can make the balloon either go up or go down. Okay, so that's how it works. So it's all based on the ideal gas law that we just learned. Okay. All right. So now let's move on to the next topic on kinetic theory. So we just look at the relationship between those quantities describing a collective of air. So those are called microscopic quantities. So because it's a collective parameter describing the air. So like pressure, temperature, right? Um, And then these are all related to the microscopic quantity like position and velocity. Okay, so a few assumptions here before we dive in. So we are assuming that air molecules are identical with mass of m, and we'll treat them as point particles. Okay, they have a fixed volume of v. That means it's inside a container, and so air molecules, they typically move randomly and always obey Newton's laws. Um, one more assumption is collisions with other air molecules and walls are elastic. So that means they're not losing the kinetic energy when they collide into the wall or into each other. Okay, so those are the assumptions. So let's take a look on a container, a cubic container here, as shown in this slide here. So cubic container, and it has the side length of L, and then we are just going to now look at the two-dimensional here in this case. That means it just in X, Y direction or Y, Z direction or X, Z direction, okay? So let's assume there's an air molecule is moving to the left and then it hit the wall, it comes back, okay? So for this particular event, so you'll see that the velocity changes direction, although it does not lose the kinetic energy. So that means how much kinetic comes in should be equal to how much it comes out here. So V magnitude is not changing, but direction changes, okay? So initial momentum should be minus mvx, and then final momentum is mvx positive, because to the right to be the positive direction in that case, okay? All right, so now this guy hit the wall, it turns direction, that means there's a force on the air molecule. Now, according to Newton's third law we learned last semester, we know that, so if the wall exert force on the air molecule, then the molecule will exert force on the wall as well. Okay, so then this collision gives you a force on the wall. Now, by just these molecules, then there's a pressure exerted on the wall during this collision, which is the force divided by the area of this wall. Okay, so this is cubic, so then each side is a square. The area should be L square. The force here should be equal to, if you remember, this is an impulse momentum theorem because there's a momentum change. So mvx minus of mvx. Okay, so total moment change should be 2 times mvx. Now it hits this guy, this wall here, it will bounce back and then hit the other wall and then comes back. Okay, so then you'll give this wall a second collision. So that means the time it takes for each collision to happen. So that would be the distance the molecular travel in the round trip to this wall and back. So that's 2L divided by, so the time it takes to be 2L divided by Vx, okay? So that's T, momentum change is 2 times mvx. So basically 2 mvx divided by 2lvx, that would be the force. So 2 and 2 basically cancel, okay? And then this Vx in the denominator will come up. So they get mvx square over L. Okay, so this is how you calculate for the force according to impulse momentum theory. Okay, so first figure out the momentum change for this collision and then how often the collision happens, which means how much time for the round trip. Okay, momentum change divided by T, that gives you force. All right, so that's L here divided by L squared, that gives you L to the Q. Now L to the Q should be the volume of the container. Okay, so then pressure exerted by each molecular is equal to mvx squared over V. Okay, so mv squared over V for the pressure of each molecular exerted. Then if we multiply by m moles of here, because there will be a capital M molecules involved here in the box, okay? So that will give you total pressure of the collective gas. It's m moles times that m times each molecular's pressure on the wall. So that gives you m times, this is the P for each individual molecular, okay? So then P total pressure equals to this guy. Okay, multiply V to both sides of the equation, give PV equal to mvx square. Okay, and here mvx square you can actually multiply by 1/2 and multiply by 2, so that get rid of the basically you are multiplied by 1. But if you are doing that trick here, this guy is the kinetic energy. If you remember, kinetic energy is 1/2 mvx square and then 2m over here. So P, pressure times volume, equals 2 times total number of molecules times the average kinetic energy just in x direction, okay? Now, the molecule could be moving also in the y and z direction, so there will be other two components of kinetic energy that will add up here. So Because each molecule exerts a pressure of this much mvx square a average over V, so then total pressure of the whole gas is n times of that, okay, which is this guy. Each direction you'll have a V component in that direction, so in x, y, and z, so then total will be the x squared component, y squared component plus z squared component, okay? Now, in all these x, y, z directions, we say they are actually um, indistinguishable. That means that they are in x direction, y direction, and z direction. They will have the same average velocity score. Okay, so in that case, so then um, this guy for one component of mvx square, that should be just 1/3 of the total. So this is the total. Okay, so this is the total. This is total here without any component. So then one component x should be 1/3 of it. So total pressure then is 1/3 of total number of molecules divided by the volume times mv square av. Okay, so you can see here the pressure of the whole gas. This is a macroscopic quantity. Okay, it's proportional to then the kinetic energy or average kinetic energy. Okay, because 1/2 mv square average is the average kinetic energy of the molecules. So we are connecting the macroscopic P with the microscopic kinetic energy of each molecule here. Looking back at this equation, we got a couple slides back over here. Okay. PV equal to that, 1/2, 2n times 1/2 of mvx square. So then in this case, this is the kinetic energy square, but PV equal to also NKT according to ideal gas law. Okay, so if you can look at PV equal to that and then PV also equal to that. So you can say this guy then equal to this guy. So basically this one. So capital N and capital N will cancel and you'll see then, or actually here, this is different one. Again, we are doing the same trick here, 1/2 KT over here, 2n here. So then this whole thing equal to this thing. Okay, so 2n and 2n basically cancel. So this guy, the average kinetic energy in one dimension, then is equal to 1/2 KT square. Okay, so it's 1/2 and then Boltzmann constant times the temperature of the whole gas. Okay, so again, this is average individual molecules kinetic energy in one component, and then this is the temperature of the whole gas. Okay, so there's connection between the microscopic individual molecules to the macroscopic, the whole collection of gas here. So the kinetic energy is proportional to temperature. Okay, and again, each dimension x, y, z, they should have the same kinetic energy average. Okay, so then total will be 3 times of this guy. So for the average translational kinetic energy in 3-dimensional should be you should multiply by 3 because it's 3-dimensional. Okay, there are 3 dimensions. You multiply by 3 for each dimension. And for the total kinetic energy, this is just one molecule. For the total kinetic energy of the whole gas, then you multiply this guy by m. So then this is 3/2 nkt. Again, if you use moles instead of each individual numbers of molecules here, using moles here, then nkt becomes nRT, just like PV equal to nkt or PV equal to nRT. Okay, so either way. Average velocity of molecules, this is total average. That means you have the x, y, and z component already combined, should be equal to just 3 kT divided by small m. In this case, m is the mass for each individual molecule. Okay, or you can write it in terms of RT over capital M. Okay, so you multiply numerator and denominator both by Avogadro's number. At the bottom here, that gives you molecular weight. molecular mass. Okay, on the top here is 3RT. Okay, so then V square average speed of molecular square is 3RT over M. Okay, so it depends on what you are using. You can use Boltzmann constant, individual molecular mass, or you can do gas constant, then you are doing the molecular weight or molecular mass of the air. All right, so then if you take square root of this guy, that's the definition of root mean square quantity, then that should be equal to square root of 3RT over M. Okay, so root mean square velocity of the gas is square root of 3RT over molecular mass. Okay. All right. Now in reality, not every molecules are traveling at the same speed, right? Some of them should be going at larger speed, some of them should be at a small speed. But any collection of gas, the speed distribution will be following the Boltzmann's distribution. Okay, so that means some will be slower, some will be faster. Okay, and the root mean square will be somewhere here. You can calculate it. Okay, so this is at 300 Kelvin and then 1100 Kelvin. Okay, so if you have larger temperature, you can expect overall they are moving faster than lower temperature. All right. That's about it today. So what we learned today, first, that's the ideal gas law, two expressions, PV equal to nRT or PV equal to capital NKT, okay, Boltzmann constant or gas constant. And kinetic theory of gases. So the kinetic energy of individual molecules is related to the temperature, also related to the pressure of the whole gas. If you are looking for the root mean square speed of the gas, you can do square root of 3RT over capital M. In this case, you are using molecular weight. Or you can do square root of 3KT, where K is Boltzmann constant over small m. M will be the mass of each individual one. Okay. That'll be it for today. I'll see you guys next time. Bye.